Hello and welcome to this chemistry lecture series. In this video, we're going to look at chapter 14.3, which is going to focus on naming organic compounds. Now, naming organic compounds, or otherwise known as organic nomenclature, nomenclature being the science of naming things in chemistry, is going to be probably the most extensive section we're going to do in chapter 14. And that's because I'm going to go over the nomenclature for every single type of compound. Now, in your book, nomenclature is separated into the functional groups. So every functional group that's addressed in a chapter, then the nomenclature for that compound is addressed. But for us, I think it's better to go over nomenclature for every compound at the same time, because we're going to keep using the same rules over and over and over again with slight variations. So I'm going to go over the nomenclature for every organic compound and functional group that we need to know for the curriculum at once, instead of separating it into sections throughout the chapters. That's why this is going to be a much longer section than you're used to, but I think this is the best way to learn nomenclature. So let's start. Now, nomenclature is essential to learning organic chemistry because in order to learn about the reactions and how chemicals behave, we need to first be able to name them. You need to be able to talk about them. So we're going to go through all of the many rules that organic nomenclature entails. So pay attention, rewind, pause the video when you need to, take copious notes, because it is a lot of material we're about to cover. Now, the basis of organic nomenclature is going to be the alkanes. The alkanes are the most basic group of organic compounds we can have. They're hydrocarbons, meaning again that they're made of carbon and hydrogen, that consist only of single bonds, meaning they're the most basic type of compound in organic chemistry. It's just carbon and hydrogen, everything's single bonded, and they can be arranged in a number of different ways. Now, when we use or when we name different compounds, whether they're alkanes or some other type of compound, the name for the alkanes are going to become our root. They're going to become the name that we grab and we change as we go through organic compounds and functional groups. So the main set of alkanes are named based on the total number of carbons in their backbone. We discussed the backbone of a structure earlier in section 2, but the backbone is going to be the series, the chain of carbons that form the main body of the organic compound. Depending on how many carbons there are in that particular compound, we use a different root word or a different prefix, if you will. So we are going to learn for our curriculum the roots for 1 through 10. So for each number of carbons, we're going to have a different root. So meth would be the stem of any 1 carbon alkane. So on top of that, we're going to have the A and E ending whenever it's an alkane. And this ending is going to change as we go through different compounds. But for alkanes, we're always going to just grab the root and add the ane ending. So for a 1 carbon alkane, that will be methane. For a 2 carbon alkane, we'll have the eth root or prefix, however you want to see it, with the ane ending. So a 2 carbon alkane will be ethane. 3 will be prop. So propane, the stuff that we use to barbecue, that's a 3 carbon alkane. So 3 carbons in the main body, all single bonded, all with hydrogens. And then we just go from there with different roots for the different numbers. Always ane, because the ane tells us it's an alkane. All carbon, all single bonded. Bute will be the prefix for 4. 5 will be pent, like pentagon. 6 will be hex, like hexagon, so hexane, pentane. 7 will be hept, so heptane will be a 7-carbon alkane. 8 will be oct, like octagon, so octane is a 8-carbon alkane, and octane is what is found in gasoline. 9 carbons will be non, so nonane will be a 9-carbon alkane. And 10 will be dec, so decane will be a 10-carbon alkane. So again, if it is in ane, A and E, that's just going to be a basic alkane. So just carbon backbone, and we can tell how many carbons by that prefix or root, meth, eth, prop, but. And then ane tells us all single bonded, so all single bonded carbons in the main chain with hydrogens on all of them. So that's if we have alkanes, right? But what happens when these alkanes branch? Because we can actually have two different kinds, or actually more than one, two, but a few different kinds of alkanes. We can have what we call, and I'm going to draw them out here. We can have straight chain alkanes. So I'll put those here. So a straight chain alkane will be an alkane that has just one continuous carbon backbone. So, for example, pentane will be that in, again, when you'll be using skeletal formulas because they're very common. Propane, octane will be that. 1, 2, 3, 4. This will be butane. So those are all straight chain carbons. But we could also have branched alkanes. Branch alkanes are going to be the ones where we have what we call side chains. So 1, 2, 3, 4, 5. That's a pentane. But if we draw an extra CH3 coming out of it, it is now a branched alkane. So any alkane that has carbons that come out of that main chain is going to be what we know as a branched alkane. So any of these carbons will be branched alkanes. Because again, we have our main part of the chain, the longest one, but then we also have carbon chains that come off that main chain that are going to be part of our branch, or branches is what we call them. All right. We can also have what we call cyclicals. So we can also have cyclical alkanes. Cyclical alkanes are going to form rings. So hexane, for example, which is going to look just like a hexagon, or cyclopropane. So cyclohexane, cyclopropane, cyclopentane, which is going to look like a pentagon. So these are alkanes that have been kind of tied up into themselves and form rings. To show you the display formula, one of these, of for example, cyclohexane, it will be a hexagon of 6 carbons. That's why it's hexane. And then each carbon has 2 hydrogens. So it will look like this if we draw out the display formula. We'll get into the naming of some basic cyclohexanes, or sorry, cycloalkanes in a little bit. But that's a cyclical alkane. An alkane where we have the chain, instead of being just one straight chain or a straight chain with some side chains, it has folded back onto itself and created a ring. So these are the different types of alkanes. So how do we name this? Because we can name the straight chains very easily. Again, this has 1, 2, 3, 4, 5 carbons in the main chain, and they have no sides or anything. So it's just pentane. This has 1, 2, 3 carbons, so this is just propane. This has 1, 2, 3, 4, 5, 6, 7, 8 carbons, so this is octane. 1, 2, 3, 4 carbons, so this is butane. So what happens once we have a chain? So if this is propane, then what is this? Because this has, again, 1, 2, 3 carbons in the main chain, but then we have this carbon that sticks out of it. So is this going to be a butane because it has 4 carbons? But then what is this? So how do we name branch alkanes? How do we name cyclic alkanes? Let's go take a look at that. So when we look at the carbon backbone, and especially when we now start having some side chains or functional groups, we are going to use a numbering system for the backbone. Now, a carbon backbone might have branches, like I said before, might have these carbon chains that stick out of it, which means that we're going to have a smaller carbon chain, what we called earlier a side chain, coming out of those main chains, or a functional group like the OH for alcohols or the Cl for a halogenoalkane might be coming out of it. In order to indicate the location of those side chains or the location of the functional group, we are actually going to number the main chain of molecules. So we're going to grab all the carbons in the main chain and we're going to number them. The numbering should start from whichever end of the main chain is going to give the functional group the smallest number. So for example, if we have this, right, the main chain is always going to be the longest one. So by that logic, we could have the main chain be, and I'm going to highlight it here. So there's a few possible chains here. We have 1, 2, 3. That's a 3 carbon chain there. We have 1, 2, 3, 4, 5. That's a 5 carbon chain. And we have 1, 2, 3, 4, 5. That's also a 5 carbon chain, right? So which one's the main chain? Well, realistically speaking, it could be either of those two 5 carbon chains. We can use the 3 carbon chain because it needs to be the longest chain available. So we could use either the chain where we go 1, 2, 3, 4, 5, or we could use a chain where we go 1, 2, 3, 4, 5. It doesn't matter because in either case we have a 5 carbon chain where we have a side chain coming out of the second carbon in. So once we know that, once we figure out which one our main chain is, what we're going to do is we're going to start numbering it. But we're going to number it starting with the carbon closest to the side chain. In this case, we kind of have two options, one of which is correct, one of which is not. And that is that we could, if we did this incorrectly, start from the left. Why would this be incorrect? Because if we go 1, 2, 3, 4, 5, then our side chain is on the 4th carbon. And the rule says that the numbering should start from whichever end of the chain will give your side chain the smallest number. So if we did this, if we start from the left, 1, 2, 3, 4, 5, then we would end up with the wrong answer because that chain is on the 4th carbon. There's a better way of doing this. Again, if we want the carbon to be on the smallest number, then we should be starting from the right side. Because if we start from the right side, 1, 2, 3, 4, 5, then the side chain is now on carbon number 2. And by starting from the right side, we now have the longest chain, which is 5, with our carbon on the second carbon, with our side chain on the second carbon. So this gives our side chain the smallest number, whereas the other way we would have ended up with a side chain on 4, on carbon number 4. Now, again, I did mention there's a few ways of doing this. If we instead started from the bottom carbon and went 1, 2, 3, and let me actually do this in a different color because those colors are blending into each other too much. So if we start from the bottom carbon, 1, 2, 3, 4, 5, this is also correct as well. We could actually start from either this carbon or this carbon. Why? In either situation, we have a 5 carbon chain being the main backbone of the molecule, and the one carbon side chain is on carbon number 2 in both scenarios. Whether this is your side chain or this is your side chain, then we still have that side chain, which is one carbon, on carbon number 2. So in either situation, this is going to be correct. I'm going to stick to this one because that one's the one that's drawn in. But now, like I said, there's more than one way to do things. If we look at this molecule, again, if we look at the longest carbon chain, we'll have one. Actually, let me not do numbers yet. So we will have, if we look at the longest carbon chain, 1, 2, 3, 4, 5 carbons. If we instead went down, then we'll have 1, 2, 3, 4. That wouldn't be the longest chain. So the longest chain is here, it's 5 carbons. If we look at our numbering, we will start from the left because we have carbon number 1, carbon number 2, 3, 4, 5. It doesn't matter whether we start from the left or the right in this one. In this case, if we start from the here or here, we will get the exact same answer because if we start from the right side, so we number 1, 2, 3, 4, 5. The side chain will still be on carbon number 3 with 1 carbon on the side chain. So it doesn't matter which side we start from, we will end up with the same answer. So in this one, starting from either direction is the same, whereas in this one, we have to start from the right side to get the smallest number for our side chain. So, why do we do this? Why do we number the backbone? We're going to use those numbers to differentiate between both of these. Because if you haven't noticed, according to the rules we just learned, right? These are both 5 carbon chains. So these are both pentanes. So how do we distinguish between this pentane and this pentane? They're both pentanes. They both have a CH3, a 1 carbon side chain, but that side chain is on a different carbon. These are actually 2 different molecules. This pentane has a side chain on carbon 3. This pentane has a side chain on carbon 2. So these are actually 2 different molecules. So in nomenclature naming, how do we distinguish them? Well, we're going to use the numbers we assign to the backbone in order to designate what carbon a side chain or a functional group is bonded to. So we're going to have to follow a few different rules. For side chains, we're going to use the prefix that represents the number of carbons and add the YL ending to indicate they're a side chain. So we place this in front of the main root of the compound as a prefix. So what do we mean by that? So here we have a side chain. That side chain we said was a CH3. Normally a 1 carbon compound or 1 carbon chain is a methane. Oops. I cannot English today. Methane would be a 1 carbon compound. But because this is a side chain, whenever the methane is a side chain, we're not going to call it methane because it is not its own molecule. We call it a methyl. We replace a ane ending for an YL ending. The YL ending tells you that this is a side chain. So this will be a methyl side chain. So for side chains, we're going to grab that root word we learned earlier and put a YL ending. But then how do we add this to that pentane root that we talked about? Because these are 5 carbon backbones. So they're all pentane. We are going to add the methyl side chain to the front of this name. And we're going to use a number in order to say where that side chain is attached. So that methyl in both of these, because these are both CH3s, so they both have methyls as side chains, and they're both pentanes because they have 5 carbons, this is going to be methyl pentane. That methyl representing the 1 carbon side chain, and they're going to be X hyphen methylpentane. What is X? X is the number that side chain is attached to. The numbers are always going to be separated from letters by a hyphen, and this is very important to learn. Every time we have a number in organic nomenclature, we're going to separate it from any letters by a hyphen. So here, in this first example, we said we had this number, start from the right, 1, 2, 3, 4, 5. So this is again a pentane, because a 5-carbon alkene backbone, with a methyl side chain, because that methyl side chain has 1 carbon on it. If it was 2 carbons, it would be ethyl. If it was 4 carbons, it will be butyl. If it was 8 carbons, it will be octyl, etc., etc. And then we're going to use a number, separated by hyphen, to distinguish which carbon that methyl side chain is attached to. So in this case, this will be 2-methylpentane. The 2 symbolizes that the methyl 1-carbon side chain is attached to the second carbon on pentane, meaning a 5-carbon chain. That means that on this one, on the other side, if we go back to the numbering, 1, 2, 3, 4, 5 carbons, again, pentane, the methyl, the 1-carbon side chain, in this case attached to the 3rd carbon. So this will be 3-methylpentane. 2 completely different chemicals. Even though they look very similar, the only difference is the location of that side chain. These are 2 completely different chemicals with completely different names. 2-methylpentane, 3-methylpentane. So that is how we name side chains. We use the YL ending to denote that it's a side chain, with its own original root that we learned earlier. So methyl means a 1-carbon side chain. Propyl will mean a 3-carbon side chain. And then we put that in front of the backbone name, pentane in this case, with the number separated by hyphen from the methyl to say where that methyl is attached. Now, here's the issue. What happens when there are multiple side chains? What if we have 2 or 3 or 4 different side chains or just 1? Well, the basic idea is still the same. We're going to build up on the rules. And something you'll notice in this section is that the rules build up on each other. They build up on themselves. So we are going to just grab the same rules that we learned, and we're going to slightly change them according to the necessity, the need. For example, if we have multiple side chains, we are going to number all of them. So we're still going to use the YL ending to denote the side chain. So the side chain is still going to have the YL ending. That is still the same. We're still going to use the root with the ane ending for the main body of the compound. But we're going to add a few things. First of all, if the side chains are different, we are going to list them in alphabetical order. Meaning that if we have a methyl and a propyl and a butyl side chain, we're going to list those in front of the main body in alphabetical order. If the side chains are identical, so if there are 2 methyl side chains or 3 methyl side chains, we're going to use a prefix to that side chain. So either di for 2, tri for 3, or tetra for 4. So like we said earlier, we are going to have that YL ending mean that it's a side chain with whatever root we have in the middle. Well, in front of that root, if we have a 2 or 3 of the same kind, we are going to put a prefix. So for example, if it was 3 of the same kind, we'll put tri with the root il. So trimethyl or triethyl or tripropyl. If it's 2, then we put di instead of tri. If it's 3 or 4, we put tetra instead of di or tri, etc., etc. There should be as many numbers as there are side chains. So if this is a trimethyl, for example, then in front of that tri, there's going to be 3 numbers, 1 for each side chain. We're going to use commas to separate numbers from each other. So we use hyphens to separate letters from numbers, commas to separate numbers from numbers. So let's put this into practice so that will make it a little easier to understand. So let's look at this side chain right here. Well, first of all, we need to figure out what our longest chain is. So if we look at this chain, we could go 1, 2, 3, 4, but that's not necessarily the longest chain. So we try again. We could go 1, 2, 3, but again, that's even shorter. The longest chain here will be 1, 2, 3, 4, 5. So this is going to be a 5-carbon chain, meaning this is a pent. Oops, yeah, a little too big there. So we're going to actually put it up here. So this is going to be a pent. We're going to build it slowly. Everything's single bonded. We don't have any double or triple bonds. So it's a pentane is our backbone. So now that we have the pentane, we need to number this. We have two choices. We can go left to right or right to left. If we start left to right, 1, 2, 3, 4, 5, then our carbons, our side chains, will end up on carbons 3 and 4. So that's not the proper way to number this. Instead, we are going to go from right to left. Because if we go from right to left, then the side chains end up on carbons 2 and 3. Meaning we have the side chains on smaller numbers. Always remember, we number the way which gives us smaller numbers to the side chains. Another way to think about this is that we're going to number starting from the whichever end is closer to a side chain. So, once we know this, we now know that there are going to be 2 methyl side chains, because again, this is just a stick, meaning these are CH3s. So there's only 2 methyl side chains. So because both of them are, and I'm actually got this in green, but because both of them are methyl, they're both CH3 here and CH3 here, we're going to put in front of this pentane, which is the backbone, dimethyl. So to break it down again, remember, the YL tells us it's a side chain. The meth tells us it's a 1-carbon side chain. And the di tells us there are 2 of them. There are 2 methyl side chains on a pentane, on a 5-carbon chain. So once you have the dimethyl pentane, the only thing we're missing is that we need to say where these methyl side chains are. Because it could both be in carbon 2. It could be 1 in 2 and 1 in 3. It could both be in 3. We could have 1 in carbon 2 and 1 in carbon 4. So there's a bunch of different conformations that this could take. So what are we going to do? We are going to, before this dimethyl, put the fact that these side chains are in carbons 2 and carbon 3. So how do we do that? Again, we separate numbers from letters by a hyphen. And then we're going to put the 2 numbers separated by a comma. Because if we just put 2, 3, that's 23. There are no 23 carbons here. So we're going to put 2, 3 dimethyl pentane. And that is our compound. The pentane tells us 5-carbon main body with all single bonds. So the pent is 5, ane is all single bonds. Dimethyl, so di means that there are 2, meth means they're 1 carbon, YL means it's a side chain, so 2 1-carbon side chains. And then we put the numbers for where they're located. We say 2, 3 dimethylpentane because the 2 methyl side chains are on carbons 2 and carbon 3. So let's look at this one, and let's go a little faster here. Our main body here is going to consist of the longest chain again. So 1, 2, 3, 4. Even though there are 5, 6, 7, 8 carbons in total, the longest chain we can make is 4. And yeah, we could start here and say 1, 2, 3, 4. That would actually be perfectly fine. We'll end up with the exact same answer. All right. So we're going to go with the horizontal one just to make things visually easier. 1, 2, 3, 4. That's our longest chain. And now here is one of those cases where it doesn't matter where we start. Because if we start from right to left numbering, we end up with side chains on carbon 2. If we go from left to right, we end up with side chains, 2 methyl side chains on carbon 2. So it's the same thing either way. This is a very symmetrical molecule. So we're going to start with the right side. 1, 2, 3, 4. Now, like we said, and I'm going to erase this one right here now. Let me pull back my highlighting here. So this is our backbone. 1, 2, 3, 4. That's our backbone. We are going to have a 4-carbon main body. So again, 4 carbons is bute. So bute tells us that it's 4 carbons. Ane tells us that they're all single bonded. And then we have in this molecule 4 different methyl side chains. 1, 2, 3, 4. All of these are going to be 1 carbon side chain, so CH3. This is again 1 carbon, because remember, 1 stick, if it just ends there, that's 1 carbon. And carbon this has 1 bond already, so we have 3 hydrogens here. This is CH3, this is CH3. So we have 1, 2, 3, 4. So tetra. That's why I need to close. So tetra, they're 1 carbon, so they're methyl. So tetra methyl. So again, the YL tells us they're side chains. Meth tells us they're 1 carbon. Tetra means that there are 4 of them. So tetramethylbutane, but where are those 4 side chains? There's 2 of them in carbon 2, 2 of them in carbon 3. So what do we call this? 2, 2, 3, 3 tetramethylbutane. The numbers have to be in numerical order from lowest to highest. So 2, 2, 3, 3. And again, why do we put the 2 twice? Because there are 2 different methyl side chains on carbon 2. If this is tetramethyl, if there are 4 methyls, then there need to be 4 numbers in front of it, even if those numbers are exactly the same. All right. All right. So that's if we have 4 of the same side chain. Let's look at one last example to see what happens when we have a mixture of side chains. So looking at this one at the end. Again, if we look at this one, we have our longest chain, which we could start from here, 1, 2, 3, or 1, 2, 3. Doesn't really matter. So we're going to start from here. 1, 2, 3, 4, 5, 6 carbons in total. So there are 6 carbons in this compound. 1, 2, 3, 4, 5, 6. And again, we start at the left or the right side. Why? If we start at the left side, then the first time we reach a side chain will be 1 to the 3rd carbon. Whereas if we start from the right, the first time we reach a side chain is going to be the 2nd carbon. So it gives us a lower number. So we're going to start from the right. 1, 2, 3, 4, 5, 6. So because there are 6 carbons in the main body, this is going to be hex for 6, ane, because they're all single bonded. So it's hexane. Now this particular hexane has 2 side chains. There's a 2 carbon side chain. So if we look at this one, we'll make this one green. So this, actually, I'm making this one green. So this one is CH3 because it has just 1 stick. So that's 1 carbon. Whereas this one, which we'll put in pink, is going to have, actually, let's do this in yellow, is going to have 1, 2 carbons. So this right here represents CH, Let me put that on the side so we can see a little better. So that's going to represent CH2CH3. This is a 2-carbon side chain. So it's ethyl. So instead of ethane, which will be a 2-carbon alkane, this is ethyl, YL, because it's a side chain. It's a 2-carbon side chain. On the other hand, the 3-carbon side chain we have on the other side is a methyl. Now the methyl side chain is on carbon 2, while the ethyl side chain is on carbon 4. So which one do we write first? It doesn't matter what number they're in. Just because methyl is in carbon 2 does not mean it goes first. When we put these here, we're going to put them in alphabetical order, meaning that methyl comes second because it starts with an M, and ethyl comes first because it starts with an E. So what is this going to be? This is going to be ethyl methyl hexane. So here I'm going to put the methyl first just because. So methyl, we said, is in carbon 2. Ooh, that is too big. Methyl is in carbon 2. And it has to go second in the list or closer to the root word because it's second alphabetically. So this is going to be methyl hexane. And because it's in carbon 2, we're going to put hyphen 2-methyl hexane. But because we also have the ethyl group before that, and again, alphabetical order, we need to put another hyphen because we're going to have words before this number 2. And those words will be ethyl. So this will be ethyl because we have an ethyl side chain. And that ethyl is in carbon 4. So this will be 4-ethyl 2-methyl hexane. So it's a lot to unpack, right? The prefixes or the side chains are in alphabetical order, eth versus meth. So hex tells us 6 carbons in the body of the compound. Ane tells us they're all single bonded. Methyl tells us it's a 1-carbon side chain. 2 means that this is in carbon number 2. Ethyl tells us it's a 2-carbon side chain. And the 4 tells us that this is in carbon 4. So if we were to draw this from scratch, we would draw a 6-member ring. 1, 2, 3, 4, 5, 6. We will then see that it says 2-methyl. So in carbon number 2, we would write a 1-carbon side chain, so stick. And then 4-ethyl, meaning that in carbon number 4, we will write a 2-member or 2-carbon side chain. So this is 4-ethyl 2-methyl hexane. Again, very important to remember. Letters are separated from numbers by hyphens. So notice how that 2 has hyphens on both sides because it has letters on both sides. Whereas the 4 only has a hyphen on the right side because there's no letter before it. All right. So that's how we name alkanes when we have multiple side chains. So let's keep track of all of that because you will be using this over and over again. Now, what are the different types of hydrocarbons? We already talked about this briefly earlier, but there's 4 different types of hydrocarbons. Now, there are 3 different types of branching of the main body. So we can have straight chains, branches, or cyclicals like we talked about before. But hydrocarbons also come in variety of bonding. Meaning we could have a alkane, which is a hydrocarbon where all of the bonds are single bonds, and it's a straight chain or even a side branched, but it will be everything single bonded. We could have alkenes, E, which we talked about before, where at least one of those carbon-carbon bonds is a double bond. Alkynes, by the same logic, are hydrocarbons that have a triple bond somewhere in their body. And then cyclicals are carbon chains that form a closed ring, like what we saw earlier. So this is a cyclopentane where the cyclical has a closed ring, meaning that the end carbons, instead of being just in a straight line, attach to each other. The naming convention we have been using is going to apply to all of them. We saw it with alkanes, but it still applies with alkenes, alkynes, and cyclicals with slight variations. So what we're going to do now is, now that we have the basis of everything, the numbering, the side groups, the side chains, the main body, how do we number it, let's look at how would we go about altering things if we had an alkene, or if one alkyne, or a cyclical, or functional groups later on. Each of these types of hydrocarbons have their own unique naming conventions that tweak, that change slight variations to the main alkane groups that we just saw. So again, don't think of this as whole new ways of naming, but of variations, of slight changes that we're going to have as we change what we're looking at, whether it's an alkane, alkene, alkyne, or a cyclical, or functional groups later on. So let's look at alkenes first. So if you remember, alkenes have a double bond somewhere in them. So these are all examples of alkenes. And they contain double bonds with the general formula CnH2n. So we're going to have twice as many hydrogens as carbons if they only have one double bond. Alkenes are going to be named almost identical to the alkanes, only we need to change the ending. Instead of using an ANE ending, like in alkane, we're going to use an ENE ending, to no one's surprise. Because again, that ENE ending tells us it's an alkene. Now, if that ENE ending is there, if the double bond could be placed in multiple different locations, then we need to put a number in front of the compound name or in front of the ENE for the alkene to locate the double bond. And why is this? Organic nomenclature is about being as specific as possible. So if we look at a molecule, we're going to look at this molecule right here, propene. This is a very simple molecule where we have 3 carbons, 1, 2, 3, with a double bond. So whereas a 3-carbon chain will be propane if we have no double bonds. If we add a double bond here, then propane to change to alkene simply becomes propene. So we simply change that A to an E, and propane becomes propene, meaning it has a double bond. And that's it for that one. Why? There's nowhere else we could put this double bond. If we drew this with a double bond on the other 2 carbons, notice this is the exact same molecule. They're the exact same molecule, but flipped over. We have just rotated this around a vertical axis by 180 degrees. So it's just the same thing, but flipping it over, right? It's just rotating it over. So these are exactly the exact same molecule. They're not different compounds. So there is no 2 different ways of writing propene. So we can just call it propene. However, if that compound can have the double bond in different places, we have to specify. So let's look at these 2 right here, because this is a perfect example of this. These are both 5-carbon straight chains. So we have carbons 1, 2, 3, 4, 5. So that will be pent-ene instead of ane because we have a double bond. 1, 2, 3, 4, 5. So both of these are pentenes. But what's the issue? We can't just call them pentene, because if we call them pentene, that would assume that they're the same molecule, and they're not. If I told you to write a pentene, to draw a pentene, you would draw 1, 2, 3, 4, 5 carbons. But then where will you put the double bond? Will you put it here? Or will you put it here? Or will you put it here. Actually, that's the same one. Yeah, that's the same one. So that one don't count. So which one will you do? There are two different ways of, or two different places you could put this double bond. And that's why we need to actually state where the double bond is. So in this top one, the double bond starts, and this is very important, we put where the double bond starts, the lower of the two numbers, because the double bond's between two carbons. This top one, the double bond starts on carbon number 2. So we will call this 2-pentene. Or an alternative, another way of naming it, that will be pent-2-ene. Both of these are correct names. This one, where the double bond starts in carbon 1, will be 1-pentene or pent-1-ene. Again, both of these are fine names. You can use either or. Unlike propene, where there's only one place to put the double bond, with pentene there are two different locations to put the double bond. So we have to specify whether it's 2-pentene, meaning the double bond starts at carbon 2, or 1-pentene, meaning the double bond starts at carbon 1. Now, double bonds are again numbered based on the location of the lower carbon. So if you have this one double bonds between carbons 2 and 3, so we say it's on carbon 2. This one is in between carbons 1 and 2, so we say in carbon 1. If you have multiple double bonds in your molecule, like this bottom one, we are going to use the same ideas that we did earlier. So we are going to number all of them, and we are going to use a prefix if we have more than one. Why? Because if we have more than one double bond, then we need to show that in the name. So looking at this compound right here, we have, if we number these, and again, if we have double bond, you always want it in your main chain. So it's carbon 1, 2, 3, 4, 5. So again, this is, and I'm going to erase this at the top so they don't get in our way. So here we have a 5-carbon chain. So it's going to be pent. Now, it is a pentene because we have double bonds, but we have 2 double bonds. So this is going to be a pent-diene. The di means from before that we have 2 of the group. So the ene tells us that it's an alkene, a double bond. The di tells us there are 2 double bonds, not just one. So this is going to be pent-diene, because there are 2 of them. And because there are 2 of them, we need to number both of them. Since we started with, oops, actually I started on the wrong side, and I just noticed this. Because if we start here, then the first double bond is in carbon 2, but if we start from the left side, 1, 2, 3, 4, 5, then the first double bond is in carbon 1, so it's a lower number. So this is going to be carbon, the first double bond is in carbon 1, the second double bond starts at carbon 3. So this is not going to just be pent-diene, it's going to be 1, 3 pent-diene. And the reason I left the space there is because we need to also add a side group that we have here. So this side chain, which is a CH3 side chain, so this is a methyl side chain, is also in carbon 3. So this will be 3-methyl, like we saw before, 1, 3 pent-diene. Or if we wanted to put that 1, 3 in front of the diene, it will be 3-methyl pent hyphen 1, 3 hyphen diene. So again, every part of a nomenclature in organic, it has a purpose. Ene tells us there's double bonds. Di tells us there are 2 of them, 2 double bonds. Pent, 5-carbon body. Tells us what the body, let's do this, body. The 1, 3 tells us the location of the double bonds. And then the 3-methyl tells us the YL tells us it's a side chain. The meth tells us is 1 carbon. And the 3 tells us the location of the side chain. So every single part of this name has a purpose. It has something that it's telling us. So if we wanted to draw this from scratch, we would again look at that root word. So if we were instead given the name and asked to draw it, we will look at the root, say it's okay, pent means 1, 2, 3, 4, 5 carbons. Diene means that there are double bonds on that chain. So where are those double bonds? On 1 and 3. So carbon 1 has a double bond. 2, 3, carbon 3 has a double bond. And then the fact says 3-methyl tells us that carbon 3 also has a methyl side chain. And that's how we arrive at the exact same molecule. That's how organic nomenclature works. It's called IUPAC naming. It has a lot of rules. It's very specific so that when someone reads this, they all end up with the same molecule they're drawing. All right, so let's go into alkynes. And alkynes are basically just the exact same thing we just talked about with alkenes, but they have triple bonds. So because they have triple bonds, they are going to have a different ending. Because alkynes end in YNE, then alkynes are going to have the same hydrocarbon naming as the alkenes, but instead of ANE, we're going to have YNE. So ein instead of ein. The rest of the naming convention is exactly the same as we saw for alkenes. So we're going to use the same ideas here. If we have the triple bond that cannot be anywhere else, like in propyne, then we don't need to put the number. If it can be in 2 different places, like with 2-pentyne and 1-pentyne, then we need to use the numbering to denote where that triple bond starts. So here starting at carbon 1, here starting at carbon 2. So it's 2-pentyne, it's 1-pentyne. Or again, that can go in front of the ending. So it could be pent 2-ine and pent 1-ine. Both of them are fine names because they have the same connotation. You will end up with the same molecule. And then if we have multiple triple bonds like we do here, 1, 2, 3, 4, 5, 6, like hexdiene, di meaning that there are 2 triple bonds, Y and E telling us the triple bond, hex because it's 6 carbons. We do need to put the location of them because this could be in multiple different places. It could be in 1,3 or 1,4. It could be in 1,2. So we have to put those numberings. And then there's a methyl side chain that goes in carbon 5. So there's nothing different in alkynes with triple bonds than in alkenes with double bonds other than the ending. Instead of an ENE, which we use for alkenes, we have a YNE with alkynes when we have triple bonds. And then there are cyclicals before we start looking at a few other more crazy things like our aromatics and functional groups. Cyclicals are, like I said earlier, going to be hydrocarbons whose carbon chains make a ring and connect. Cyclicals can be a little more difficult because they have attachment all throughout the ring. So cyclical compounds are essentially going to be fairly easy to name if they're simple, because all we need to do is add the cyclo prefix to their name. So cyclopentane, for example, that cyclo prefix tells us that it's a cyclical. Pentane, just like we did before, tells us that pent is a 5 carbon. Let me fix that. So pent tells us it's a 5 carbon. Ane tells us that they're all single bonded. So cyclopentane is just a 5 carbon ring. And cyclicals are kind of fun in the sense that if it's pentane, it's going to be in the shape of a pentagon. If it's cyclohexane, it's going to be in the shape of a hexagon. If it's cycloheptane, it's going to be in the shape of a heptagon. It's because since that's the number of carbons, it's also a number of vertices, which is what the shapes are named after. So cyclopentane, very simple. It's going to just be the 5-carbon ring. So we just close and we make a pentagon. Remember, each one of these carbons, though, does need to have 4 bonds in total. So even though we only see 2 bonds on this carbon, that's because there are 2 hydrogens here. And that's true, unless we see something attached to them, that's true of all cyclicals. They have 2 carbons in each, 2 hydrogens in each carbon. If a cyclical compound contains double bonds in it, we use the ene ending like we would with any alkene. So for example, here we have cyclohept 1,3-diene. Instead of calling this cycloheptane, we use the ene ending because we have double bonds in the cyclical. Doesn't make it not a cyclical. You can have something be a cyclical and an alkene. And something you'll realize is that all of these groups that we learn about in organic chemistry are not mutually exclusive. So you can have a compound that has a double bond and a triple bond. Doesn't make it an alkene, or not an alkene, doesn't make it not an alkyne. It's both an alkene and an alkyne. If we have something that's a ring and it has double bonds, it's both a cyclical and an alkene. It can be both. They're not mutually exclusive. So cyclohept 1,3-diene, again, it's all the same rules that we're reusing here. The cyclo is a new part. We call it cyclo at the front prefix because it is a closed ring. It's a cyclical. Hep tells us that there are 7 carbons. Diene tells us that there are 2 double bonds in the chain. And then the 1,3. Now this is the part that's difficult. How do we number them? If there is one side chain or functional group on the cyclical, then the carbon is automatically carbon 1 and we don't have to say anything about it. But if there are multiple side chains or functional groups, like these 2 double bonds, then we need to go in the direction that gives us the lowest numbers. Meaning that one of these is always going to be carbon 1. And then we choose to go in the direction that's going to give us the lowest numbers around that ring. So let's say we choose to go here, carbon 1. And we could have chosen this, it doesn't really matter. If we go around this way, then that's carbon 2, 3, 4, 5. The next double bond wouldn't be until carbon 5. However, if we go around the other way, and we go 1, 2, 3, 4, 5, 6, 7, then these, if we go this way, then the double bonds are on carbons 1, because remember, we do double bonds by where they start, and carbon 3, meaning that we have 1,3-diene. And then cyclohep tells us it is cyclical. So if we look at that, we always are going to name a number these so that we start with the number in the lowest conformations. So we start so that it gives us the lowest number, and then we go around the ring in that way. So yeah, so that's the 1,3 cyclohept 1,3-diene. So if we look at this one right here, again, very similarly, the cyclo part of the name tells us that it's cyclical. Cyclohexane tells us that it's a 6-carbon cyclical alkane, so 6 carbons in a ring, all single bonded, so it's a hexagon. For methyl, remember, methyl means a CH3, a 1-carbon group, 1 ethyl. And ethyl means 2 carbons, so CH2, CH3. So when we draw a ring, so we will draw it, if we see cyclohexane, so it's 1, 2, 3, 4, 5, 6, so it's a hexagon. 1 ethyl means that in the carbon number 1, and we can choose any of these to be carbon number 1, really, it's up to us. It's going to be a 2-carbon chain, 1, 2. So that's carbon 1 with a 2-carbon chain. And then we can go whichever we want. We end up with the same answer. 2, 3, 4. We have 4-methyl. So we have a 1-carbon side chain on the other side. And you got to realize that this, had we started carbon 1 here with our 2-carbon chain, then it would have been 2, 3, 4. We would end up with this. It's the same molecule. They're equal to each other. All it is that it's been rotated this way, and you will get the same molecule. So whether it's this or this, it's the same molecule. It's just one ethyl, 4-methyl cyclohexane. So notice, even though these molecules are getting more complicated, we're still using the same rules. We use the numbers from the backbone with hyphens to separate them from the letters. We use a YL ending to show that it's a side chain. We use the root hex to show that it's 6 carbons, and the ane to show that it's single bonded. All of those come from alkanes. The only difference with the cyclicals is that now we use cyclo to say that it's cyclical. So don't see this as a bunch of different rules you gotta memorize. It's alterations to those rules, things that we add to things that we take out. The other type of compound we're going to have that's hydrocarbon are called aromatics or arenes. Now these are a little more complex because these contain what we call a benzene ring. And a benzene ring is what we have here. Benzene ring, if we look at the displayed formula, is a 6-carbon ring that has alternating double bonds. So a benzene ring has 6 carbons in a hexagon, so it's a cyclical, with double bond, single bond, double bond, single bond, double bond, single bond, alternating inside of the ring. Each one of those carbons, because they all have 3 bonds within the ring, has 1 hydrogen sticking out of it. This is what we call the benzene ring, and it's a very important compound in chemistry. There's a whole chapter dedicated to benzene and its compounds in A-level chemistry. But in AS, we're just going to look at the basics of it. So it's a functional group. So a benzene ring consists of a functional group, or is a functional group, that has these carbons that have these alternating double and single bonds in a ring. If we have one of these rings in a compound, we call that compound an arene, or an aromatic. Arenes are essentially any compound that has this ring in it. So when we look at this, one of the things you have to realize is that there's actually 2 different ways of writing this structure. We could, if we drew the skeletal formula, draw the 6-carbon ring with the alternating double and single bonds, but we could also draw it in this manner. So if you look at both of these right here, let me circle them. If we look at both of these rings, they're both technically correct. We just have the alternating double and single bonds on different carbons. In this one, the ones that were single bonds in this one are now double bonds, and vice versa. In reality, benzene is somewhere in between these, and that's what that A-level chapter is about, so I'm not going to go too much into it. But in reality, benzene is a combination of both of these structures. So oftentimes when we draw benzene, we draw it like this. And we draw it like this, a 6-carbon hexagon with a circle in the middle. Or oftentimes the circle in this picture is dashed, but you don't have to make it dashed. We just draw it like this. And that shows the combination of the 2 things with, remember, you have 1 hydrogen in each of these carbons. So any compound that has this benzene ring in it is going to be called an arene. Aromatic or aero compounds in your Cambridge curriculum are going to include compounds where the benzene ring is the main carbon chain of the structure, meaning that we are going to look at simpler aromatic or aryl compounds. So aromatic, arene, aryl, they all mean the same thing. It has a benzene ring somewhere in there. Benzene, the term benzene, is the simplest arene. It's just the carbon ring that we're looking at here, where every carbon has a single hydrogen attached to it, and we have those alternating double and single bonds. They're very special compounds. Like I said, there's a whole chapter dedicated to them in A-level. But what we're going to learn right now is just very simple. It's a 6-carbon. Our benzene is a 6-carbon ring with alternating double bonds that can be drawn in two different ways. And so we usually draw it as a hexagon with a circle in the middle to show that in reality, benzene is a combination of both those structures. And that's where we're going to leave it. What we really want to focus on, apart from just like being able to recognize a benzene ring, is how to name compounds of benzene. Naming arenes is going to be fairly similar or somewhat similar to naming cyclical compounds, but instead of using cyclo in the prefix, we are going to use the benzene as the root of the name. So instead of saying something like cyclohexane to being 6 carbons, we will just say benzene to mean a benzene ring. And then we are going to put the attachments in front of it. If there's only one attachment to the benzene ring, then we do not need to include any numbering. So if we look at this, for example, we have a 1 carbon side chain on a benzene ring. So this will simply just be methylbenzene. There's no numbering involved because there's only one side chain or one functional group. If there are more than one attachment in the benzene ring, then we have to use the numbering system from the lowest numbering possible. So for example, if we have 2 methyl side chains on a benzene ring, we will name one of these 1, or number one of these 1, one of the other one 2, because we always go on the way that gives us the lowest numbers. And then we'll just say 1, 2 dimethyl. So this is nothing new. This is just how we be numbering and calling other side chains on any compound. We use the numbering and then the di prefix with a methyl. And then we put benzene after it. So it's actually fairly simple. We just number the side chains or side groups and attach them to the benzene root. The benzene root tells us that we have a benzene ring that we're drawing. And then the 1, 2 dimethyl tells us that there are 2 methyls right next to each other, 1 and 2. If it was 1, 4 dimethylbenzene, then those methyl groups will be 1, 2, 3, and carbon 4. So being carbon 1 and 4 mean they will be directly across from each other. If there were 1, 3, then it will be 1 here, 1 here. If we have multiple different types of functional groups, like for example a chlorine with a methyl, then we do need to state where that side functional group is. So 2-chloromethylbenzene, for example, would be a benzene ring with a methyl group and then the chlorine on the second carbon. That methyl is then always going to be the first carbon because it's only 2 different functional groups, and one of them has to be carbon 1. 4-chloromethylbenzene, again, that methyl is, without saying it, in carbon 1 because one of those functional groups is always going to be in carbon 1. And then the chlorine is going to be in carbon 4. Why is the chlorine going to have the higher number instead of the methyl? Why is the methyl not the one that gets the number? We'll discuss that later on in this section. All right? So that's it for things that are hydrocarbons. That's it for things that are completely carbon and hydrogen based. Let's look at what we do when we have functional groups. When we have things that are not carbon and hydrogen, like chlorine or an alcohol or something like that. So let's move on to functional group nomenclature. So whenever we have a functional group that is not carbon-based, so not the side chains that we've been looking at, not the alkenes or alkynes, when we have functional groups, we're going to use the same hydrocarbon bases that we've been talking about. So whether we have an alkane, an alkene, an alkyne, we're still going to name it just like we would any of those compounds, but with slight alterations. We're going to use the same naming conventions, but we're going to add prefixes or suffixes for functional groups, depending on what the functional group is. So each individual functional group has its own unique alteration that we do based on what the functional group is. We're also going to number the carbons the functional groups are attached to. But now with some of these, this makes a little more sense than others. So for things I had like the halogenoalkanes, or the alcohols, or the amines, or the nitriles, the groups where we're replacing a hydrogen, that it's pretty simple. It's just which carbon are they attached to. But with things like aldehydes and carboxylic acids, which are always in carbon 1, we don't need to do that. And then esters are the most complex because they have 2 different carbon chains. So we're going to look at all of that. All right. So if we have multiple prefixes and suffixes that need to be added, we're going to add them in alphabetical order, just like we did the side chains earlier. So let's start going through these. Halogenoalkanes. Halogenoalkanes are a bit more tricky because we are going to have a different prefix we add to the organic compound based on which halogen is being added. If we are adding a fluorine or we're replacing a hydrogen for fluorine, we put the fluoro prefix. If we're putting a chlorine, we use a chloro prefix. Bromine, we use the bromo prefix. And iodine, we use the iodo prefix. So we're going to name the covalent compound, the alkane, the alkene, the hydrocarbon, like normal, but we're going to add a prefix based on which halogen we have added to it. We do need to number the prefix in order to indicate which carbon that prefix is attached to. And if there are multiple of that halogen, we're going to use those hyphenated prefixes like di, tri, and tetra. So for example, if we have here a 1, 2, 3, 4 carbon alkane, 1, 2, 3, 4, we would normally name a 4 carbon alkane butane. But because this 4 carbon alkane has an iodine attached to the first carbon, we're going to call this 1-iodobutane. The 1-iodo is added because of the halogen that was added to make this a halogenoalkane. If that iodine instead is added to carbon number 2, so if we have carbon 1, 2, 3, 4, it's still butane because it's still 4 carbon alkane, but it is now 2-iodobutane because, again, the iodine is in the second carbon. So again, it's basically we're using the same rules that we learned earlier. We're just going to add a prefix to the name based on which of the halogens we're adding. If we were to add 2 bromines to a cyclical, so if we just had the pentagon cyclical we have here, we will call that pentane. Cyclopentane, because it's a cyclical. So cyclopentane will just be the cyclical. If we're adding 2 bromines to it, then we will simply call this dibromo cyclopentane because we have 2 dibromines, bromo. And those bromines are going to be in carbon 1 and carbon 3. Because again, if we have a thing attached to a cyclical, it's always one of them is always 1. So this will be 1,3 dibromo cyclopentane. If we have an alkene, again, it's the same story. If we have a 2 carbon alkene like we do here, and this is a displayed formula that makes no difference, 2 carbon alkene will be ethene. Eth meaning 2, ene meaning alkene. If we have a fluorine attached to it, there will be fluoroethene. Now, why wouldn't it be 1 fluoroethene? Because if that fluorine was attached to this carbon, then this carbon will become carbon number 1, and it would just still be 1 fluoroethene. So there's really not 2 different places we can put 1 fluorine in the ethene molecule. So that's how we do halogenoalkanes. Depending on which halogen we're using, we add a prefix. With alcohols, it's very similar. We're still going to use all of the rules that we learned. But with alcohols, we're going to have a hydroxyl group somewhere. Now, what is a hydroxyl group? If we know from all the years of chemistry we've taken that OH minus is a hydroxide ion. The hydroxyl group is simply just the OH that we add to an organic compound. So that OH is what makes things an alcohol. So a hydroxyl group makes the compound into an alcohol. Now we name alcohols by a very similar method that we do halogenoalkanes, but instead of adding a prefix, we are going to add a suffix, specifically the OL suffix or OL ending. So we're going to add an OL ending for the alcohols for the hydroxyl group, and we're going to number that ending if we have the hydroxyl group where it could be attached in multiple places. And again, if there are multiple of the hydroxyl group, we'll either use di, tri, or tetra. So diol, triol, or tetraol. So if we have a 6-carbon alkane like we do here, 1, 2, 3, 4, 5, 6. This 6-carbon alkane would normally be called hexane. What we're going to do is, because this is a suffix that we're adding, we're going to get rid of the E in hexane, because we can have two vowels next to each other. So it will be hexan, we get rid of the E, O. The O being that alcohol. And because the OH is added to the 3rd carbon, we're going to call this 3-hexanol. Or again, just like we did with alkenes, we could say hexan 3-ol if we're saying, if we want to just show it closer to that OL that tells us an alcohol. If we have 2 OHs on the same carbon, so this will be carbon 1, 2, 3, 4. So this will be a derivative of butane, butane being a 4-carbon alkane. We will get rid of the E, so we get that butane. And because there are 2 hydroxyl groups, 2 OHs, it will be diol. The di telling us it's 2, the ol telling us it's an alcohol. Again, because this diol will have different places where those OHs could be. They could be on the same carbon, 1 and 2 and 1 and 1. We do need to number them. Because both of these OHs are in the 2nd carbon, this will be 2, 2, because remember, if we have diol, we need 2 numbers. 2, 2 hyphen butane diol. Or we could say butane hyphen 2, 2 hyphen diol. Both of these are perfectly fine names. If we have an alkyne with triple bond, same thing. If we will count the carbons, 1, 2, 3. So this will be a derivative of propane or propine, sorry. So propine would be the 3 carbons with the triple bond. We drop the E, so we propene 1O, because we have that alcohol, that OH in carbon 1. Now with this was a little different because we do have a second functional group, which is a third triple bond, which is a YN. So we will call this either 1-propine 1-O. The 1 has to be in front of the O because it is for that alcohol. But then also 1-propine, that 1 is for the triple bond, for the YN. Alternatively, we can move that 1 in front of the YN and call it prop 1-ine 1-O. And both of these names are acceptable. But yeah, so we just gotta find that root or that the main chain. So 1, 2, 3, 4, 5. And then remember that if we have multiple things, we need to put them all on there. In the case of the ending, if it's in a hydrocarbon like YN, EN for alkynes and alkenes, we put that first and then the suffix. In the case we have something like a side chain, that side chain is a prefix. So the order would matter. One will be at the end of the word, the other one at the beginning. So if we have a 5-carbon chain, that will be pentane, will be the root of this. Because we have both single bonded, we drop the E, so pentan, that's our root, Then we have an alcohol on the second carbon. So we'll have OL, because there's only one alcohol. And so it will be 2-pentanol, to say that that OH is on the second carbon. And then on the third one, we have, and actually let me use a different color. On the third one, we have a methyl group, the CH3. So it'll be on the third carbon, so it'll be 3-methyl as a side chain, 2-pentanol. Or 3-methylpentan-2-ol if you want to move that 2 in front of the OL. So again, the root of this is the same. We're still using those hydrocarbon rules. We're still using those side chain rules. We're just adjusting, because we have an alcohol, we adjust the ending and we use a suffix. Whereas for the halogenoalkanes, we use a prefix. Aldehydes. Aldehydes are, again, going to be a little more complicated, but not too much. Aldehydes are organic compounds that contain that carbonyl group, the C double bond O, with a hydrogen on one side and an R group on the other. That R group could be just a simple one hydrogen, or it could be a much longer carbon chain. The most basic aldehyde will be methanol, which is just a carbon double bond oxygen with 2 hydrogens on it. A common name for methanol is formaldehyde. And this is something that I wanted to bring up. Realize some chemicals have common names, kind of like how we called H2O water. Water is not a name that comes from the rules. It's a name that comes from just common use. So this will be methanol in its proper name, or formaldehyde is a common name. But why methanol? When we have an aldehyde, we use the AL ending instead of a prefix like we would with a hydrocarbon. We get rid of the E on the hydrocarbon and put AL as the ending. So very similar to what we do with the alcohol. So methanol, meth means 1 carbon, al means aldehyde. So it's a 1 carbon aldehyde. Now we're never going to put a number in front of this. The carbon for the aldehyde is always carbon number 1. So aldehydes, that AL and aldehydes will never have a number in front of it, because that number is always number 1. There's one other functional group that does this, which are carboxylic acids. We'll see later. But that's always going to be the case with the aldehydes. The carbon of the carbonyl is carbon 1. We do not need to number the suffix, so we're going to leave it like that. That's what we call a terminal carbon. Terminal carbon means that they're the last carbon of the chain, or the first one, technically speaking. They're going to be at the very end of the chain. And aldehydes, because they have the carbonyl with a hydrogen, they're always at the end of the chain, because you can't attach anything to hydrogen. You can only form 1 bond. So if we have something like this, where we have our aldehyde with a 1, 2, 3, 4 carbon chain, 4 carbons will be butanol, because we have that AL ending to the but root word, which means 4. And then we have an methyl group on carbon 3. So because of that, we will need to attach that to this. So it will be 3-methyl butanol. So the 3-methyl comes from the side group, and then the butanol, but comes from the backbone, and the AL comes from the fact that it's an aldehyde. So this, sometimes you will see skeletal formulas like this one, where the H on the aldehyde is actually shown. And this is a very common thing that you might see. It's called a hybrid structure, because we're mixing displayed formulas with skeletal. But if it was a purely skeletal formula, we would not have the hydrogen showing like in this one. In this case, we have a 1, 2, 3 carbon. So it's propan, because they're all single bonded. And then the AL is there because we have an aldehyde that can only be at the end. So instead of OL, like we do with alcohols, with aldehydes we put an AL. And we do not need to worry about numbering because it's always terminal. Aldehydes, that C-double-O-H is always going to be at the end of a chain. Ketones, on the other hand, ketones are not going to be at the end of a chain. Ketones are not terminal and therefore do need to be numbered. Ketones are going to have that carbonyl group in the middle of a chain. Now, before we saw ketones as being a carbonyl with a side chain on one side, with a chain on one side of carbons and a chain on the other. But you have to realize if we have two chains of carbons connected by a carbon, it's really just one solid chain. So propanone, for example, if we look at the carbonyl, so let me get my highlighter here. If we look at the carbonyl for propanone, then we have the C-double bond O. And we said that we had one carbon chain sticking out of one side of the C-double bond O and another carbon chain sticking out of the other side. But that's not actually a good way to look at ketones. It's helpful for looking at the general formula, but not for looking at actual compounds. A better way to look at ketones is that we have just one straight carbon chain with a carbonyl bond sticking out of the middle, or somewhere in the middle. So we see this as a 3-carbon chain, which will give us that prop root, prop and, because they're all single bonded, and then we number where that double bond is. And we're going to use the ending ONE for ketones. So this will be prop and own because a ketone. Now, why does propanone not have a number? The only carbon in propanone, or these three, that can have a carbonyl group is the central carbon. Because if we put in one of the terminal carbons, the ones at the end, this wouldn't be a ketone anymore, it will be an aldehyde. The carbonyl group being at the end carbon will make this an aldehyde. So the only one that can have this, C-double bond O, is that central carbon, so propanone does not need a name. But if we have a longer ketone, then we do. So if we look at, for example, this one right here, we have a 1, 2, 3, 4, 5, 6, 7, 8 carbon chain with multiple carbonyl groups sticking out of it. So that makes it more complex. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 2 carbonyl groups. So this makes it a dione, because it's a diketone. We have 2 of those carbonyl groups sticking out of an 8-carbon chain. So the dione is from the fact that we have 2 ketones. It's an 8-carbon chain, which gives us that octane, because they're all single bonded. So that means 8 carbons in the main body. And then we have 3,5. These 3,5 comes from the fact that the carbonyl groups on the ketone are on the 3rd and 5th carbon. So this will be 3,5 octane dione, because there are 2 ketones, so 2 carbonyl groups, or octane 3,5 dione, depending on where you want to put those numbers. But you can put them in either way. Now, unlike aldehydes cannot be in a cyclical, but ketones can be in a cyclical. Unlike aldehydes, ketones can be in a cyclical, and this should be an O. And we're going to use the same naming convention. So this is a 4-carbon cyclical. So that will be cyclobutane will be the name if there was no ketone. But because there's a ketone, all we're going to do is we're going to get rid of the E and put the O and E ending. So cyclobutanone. So we replace that ending with, or we add the ending of O and E. But the rest is the same. We still use those same nomenclature rules that we learned earlier. So that's for ketones. Slightly different than aldehydes, and we do need to put a numbering unless it's something like propanone. Next, we're going to look at carboxylic acids. Now, just like aldehydes, carboxylic acids are terminal. Why? Because after we have that carbon double bond oxygen with the OH, we cannot add any more carbons. So these are going to be terminal, meaning that the ending will not need a number on it. All right. So what ending do we use for carboxylic acids? Carboxylic acids are going to have the COOH in the structural formula, representing that carbon double oxygen OH. And we're going to use, to represent them in nomenclature, the oic acid ending. So carboxylic acids are easy to spot when we have the names because they're literally going to end with the word acid. So we're going to use a oic acid ending to symbolize a carboxylic acid, getting again rid of the last E, and because they're on the alkane, and because they're terminal, we don't need any numbering for it. The carbon on the carboxylic acid is always going to be carbon number 1. So in this case, the COOH, that's carbon number 1. COOH, this is carbon number 1. COOH, this is carbon number 1. It's really the only carbon. And now, here's the funny part. When we have a dioic acid, we have a 2-carboxylic acid, it doesn't really matter which one we call carbon 1. We just need to choose one of them. So, again, if there are multiple, the reason this is ethanedioic acid. Eth means 2 carbons. So this is 2 carbons, alkane, so they're single bonded. Because we have that AN. And di means 2 oic acid, which is carboxylic. So dioic means 2 carboxylic acids, 2 C double bond OHs. Because each carboxylic acid has a carbon, that means ethanedioic acid is just simply COOH attached to COOH. Because we have now 2 carbons. We do not need to number the carbons because there's only 2 of them. If we have something a bit more complex like this, we have carbon 1, always start from the carboxylic acid, 2, 3, 4, 5. So we have that pent and coming from the 5 carbon main body that has nothing but single bonds. Oic acid comes from the fact we have a carboxylic acid. And that carbon is always going to be carbon 1, so we don't need to number it. And then we have, in carbon 3, we have a 2-carbon side chain. So because that side chain is 2 carbons, it's eth. And because it's a side chain, it's ethyl. So this is 3-ethyl pentanoic acid. If we have a 1 carbon, that's easy. It's methanoic acid because it's just meth means 1 carbon. Formic acid is the common name for that one. It's the same way that we have formaldehyde for the aldehyde. And that's actually a fun fact. This is what ant venom is made out of, formic acid. Butanoic acid, same thing. 1, 2, 3, 4. So the but comes from the fact that you have 4 carbons. And because they're all single bonded. And then the oic acid comes from the fact that we have a carboxylic acid. Again, this is not 1 butanoic acid because that is the only place this carboxylic acid can be. We cannot have the carboxylic acid in any carbon that is not carbon number 1. All right? So, that's carboxylic acids. And now we're moving on to probably the hardest out of the functional groups, esters. Esters can be difficult because they have 2 different carbon chains. We had also described ketones as having 2 carbon chains, but esters truly have 2 carbon chains. We have what we call the carbonyl carbon chain, and that will be the one that is that the carbonyl group is involved in. So the carbon chain that comes into the carbonyl, and then we have the oxygen carbon chain, the one that's attached to the oxygen that's attached to the carbonyl. So with these, it's actually kind of difficult because we are going to have multiple parts to the name. And there's actually a space in this one between the 2 names. So we're going to have the side chain. Let me actually match the colors here so that they make more sense. We're going to have what we call the side chain, which is going to be our O chain. The carbon chain attached to the R, that's our side chain. It's not the main part of the ester. The main part of the ester is going to be the one that's attached to the carbonyl group. So this C double bond O with the R, this is going to be considered our main chain for that compound, for that ester. So we do gotta see esters as two parts. All right, the OR part and the carbonyl part. So we're gonna name this separately. First, we're going to name the side chain of the carbonyl as if it was a side chain. So we're going to look at that chain attached to the oxygen, and we're going to name it using a YL ending. So in this case, we have a 1 carbon side chain in this ester. And again, we can see it's an ester because we have a COO with carbons on both sides. This is a 1 carbon side chain. Meaning it's a meth, because it only has 1 carbon, ill, because it's the side chain. So that's going to be the first part of the name, methyl, denoting that O chain. And then in green, over here, we're going to have the main chain. The main chain here, including the carbonyl carbon, is going to consist of 2 carbons. So because this one consists of 2 carbons, again, it's going to be eth. Because they're single bonded, it's going to be FN, because we got rid of the E. And that's where we're going to use this other ending. We're going to use the O8 ending for the main chain to show that that's the main chain of the ester. So because they're 2 carbons, single bonded, FN, and then we're going to put the O8 ending. This is always going to be carbon 1, so we don't need to put numbering here. So this we're going to attach after the side chain. So this right here will be methyl ethanoate. And that's it. I mean, we're essentially going to look at those side chains and do this for all of them. If we look at this one, we have our carbonyl here. Carbon 1, 2, 3, 4. And again, the carbonyl carbon is always carbon 1. So it's a 4-member chain. So it's going to be but for 4 carbons. And because they're all single bonded, O8 because it's the main chain. And then on the other side, here we're going to have a 2-carbon chain. So that's F. And because it's a side chain, it's the one attached to the oxygen, it's ethyl. So the side chain is ethyl, the main chain is butanoate, so this is ethyl butanoate. Let's do one more. If we look at this one, again, the side chain does not necessarily need to be the smallest. So if we look at the O chain here, we have 1, 2, 3, 4. So our quote-unquote side chain here has 4 carbons. So we're going to use a but root, single bonded, so butan. Oh, sorry, butyl, not butan. So we have 4 carbons, and if we was double bonded somewhere, we would put butan-il. So butanil, or butyl. So butyl, and then a 2-carbon side chain, meaning that this will be what carbons, oops, where did my door go? Carbon 1 and carbon 2, butyl, eth, and, because it's single bonded, O8, because even though this is a shorter chain, it's still our main chain because it has a carbonyl group. So this will be butyl ethanoate. So we gotta remember, we name the side chain based on what's attached to the oxygen, and then the main chain based on what's attached to the carbonyl group. The main chain will get the O8 ending, this side chain the YL ending. So that's esters, which are probably the hardest to name. Then we have amines. Amines are going to be, again, one of those where we're just replacing a hydrogen for our group. In this case, the NH2 group is what makes an amine. So it's going to be a carbon chain with an H2 somewhere. And again, these are called primary amines. There are secondary and tertiary amines, but we will look at those in A-level chemistry, not in AS. We name amines by using the amine ending. So it's actually very straightforward. The whole ending is the word amine. And we're going to name the main hydrocarbon chain as a side chain. Why? With amines, it's a bit different. The nitrogen is considered the center of the compound. So what we look at is that we have the nitrogen with things attached to it. So we're going to number the suffix or name in order to indicate which carbon has the amine group. And then if there are multiple amine groups, we're going to use di, tri, tetra prefixes, although that's a very rare. There are many types of amines, like I said, but we're only going to look at these primary ones here. So for example, we have here a 5-carbon chain. 1, 2, 3, 4, 5. We would normally name this pentane. But because it's an amine, they have a special nomenclature to them. We are not going to use the ane ending. We're going to use the YL ending. We are going to essentially assume that the carbon chain, even though it's the main chain, is a side chain. Because the focus of an amine is always the nitrogen. So this will be 3, because the NH2 is attached to the third carbon. Pentyl, because it's an amine. If we have 1, 2, 3 carbons, again it's prop because 3 carbons, but we're still going to use YL because it's an amine. So propyl amine. If we have 1 carbon, methyl amine. So we're going to use the same things that we did for alcohols, but instead of using that AN or EN or the AN and EN ending, we're going to use a YL ending for a side chain. And then there's one more. The last functional group is going to be our nitriles. Now, nitriles are not, quote unquote, in your curriculum to name, but they are used. The names are used a lot. So we are going to very quickly go over them. With nitriles, again, nitriles are going to have that CN, C triple bond nitrogen attached somewhere where the hydrogen should be. In order to name a nitrile, we're going to use the name nitrile, just like we did with the amines. But we are not going to use a YL ending that we did earlier. So we do not need the number suffix, as the CN group can only be found in the terminal carbon. So because we have that CN group, that has to be a carbon, it has to be part of the chain. So the carbon that has the nitrile is always carbon 1. So it's very similar to carboxylic acids and esters. This is always carbon 1, 2, 3, 4. Or carbon 1, 2, 3. Or here, carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. Apart from that, we're just going to put the word nitrile next to them. So butane nitrile will be a 4-carbon nitrile, because but means 4. Propane nitrile will be a 5-carbon alkane, because it means 5. Oh, sorry. What am I saying? A 3-carbon alkane, because it means 3. And then nonane nitrile. Nonane means 9, so that's 9 carbons. Nitrile tells you that the first carbon has a triple bond to a nitrogen. And then 2-ethyl in this case, because we have a 2-carbon side chain. So again, we're using the same rules. We're just applying the fact that we're going to use a nitrile suffix in this case. All right. So that's the functional groups. Again, it's a lot of the same rules that are stacking up on each other, and slight alterations we make as we go through the different either functional groups or types of hydrocarbon. So the best way to do this, apart from watching this a few times and making sure your notes are very clear, is to make sure you practice. If you're in my class, we have a very big packet that's already on your class online that we're going to use to practice this. But realistically speaking, you can practice this anywhere. Be aware that if you do look for online practice, this is only what's in your curriculum for AS chemistry, not the whole of organic nomenclature, which is a much wider and much bigger topic. But yeah, that's it for section 14.3. Now remember that this did go over the nomenclature for all the functional groups, which are not in chapter 14. Only the basics are in chapter 14. As we usually in the book go over nomenclature for individual functional groups and side chains in the chapters that they appear. But again, for me, I think it's much easier, since we use the same rules over and over again, to go over it all at once. That's it for chapter 14.3. I will see you all in the next video.